Explainable AI, XAI, is a transformative approach that unlocks the black box of AI systems, making their decisions transparent and understandable to humans, which is crucial for trust, accountability, and compliance in modern AI applications. By providing insights into how AI models arrive at their conclusions, XAI ensures that stakeholders can verify and validate AI decisions, preventing unintended biases and ethical dilemmas. The key principles of explainable AI revolve around transparency, interpretability, and accountability, setting it apart from traditional black box models that offer no insight into their decision-making processes. Unlike opaque systems, XAI emphasizes clear communication of how inputs are transformed into outputs, ensuring that ethical standards and user trust are maintained. AI systems that lack explainability pose significant ethical risks, such as bias amplification and unfair treatment, which can lead to discrimination and loss of trust. Mitigating these risks involves implementing transparent algorithms and robust auditing processes to ensure that AI decisions are fair, accountable, and aligned with societal values. Stakeholder perspectives on explainable AI vary widely, with developers, regulators, and users each having distinct needs and expectations from AI systems. While developers focus on debugging and optimization, regulators emphasize compliance and governance, and users seek trust and clarity in AI-driven decisions. Developers leverage explainability to debug and improve AI models by identifying errors and biases in the decision-making process, which enhances the accuracy and reliability of AI systems. By understanding how models interpret data, developers can fine-tune algorithms to ensure they perform as intended in real-world scenarios. Regulators and policymakers prioritize explainability in AI governance to ensure compliance with legal standards and ethical guidelines, which is essential for public safety and trust. By mandating transparency, they aim to prevent harmful outcomes and ensure that AI systems operate within acceptable societal norms. Explainability enhances user trust by providing clear insights into how AI systems make decisions, which helps users understand and accept AI-driven outcomes. When users can see the rationale behind AI actions, they are more likely to trust and rely on these systems in their daily lives. Real-world failures of non-explainable AI systems have led to critical errors and public backlash, highlighting the need for transparency in AI decision-making. These failures often result from unintended biases and misinterpretations that could have been avoided with explainable models. Case studies demonstrate the importance of explainability in preventing harm, such as the misdiagnosis in healthcare AI systems that led to patient harm due to opaque decision processes. By implementing explainable models, these systems can provide clear justifications for their recommendations, ensuring patient safety and trust. Fundamental approaches to explainability in AI include intrinsic and post-hoc methods, which focus on making models inherently interpretable or providing explanations after the fact. Techniques like symbolic AI and balancing accuracy with interpretability are crucial for developing AI systems that are both effective and transparent. Intrinsic explainability methods are built into the AI model's architecture, ensuring that the model's decisions are naturally interpretable, while post-hoc techniques provide explanations after the model has made a decision, often using visualizations or simplified models to clarify complex outputs. Intrinsic methods, like linear regression, offer direct insights into decision-making, whereas post-hoc approaches, such as LIME or SHAP, are essential for complex models like deep neural networks. Symbolic AI, with its rule-based models, excels in transparency and interpretability, allowing users to trace decision paths through explicit rules, but it struggles with scalability and adaptability in dynamic environments. While symbolic approaches provide clear logic and are easily debuggable, they often lack the flexibility and learning capacity of more advanced machine learning models, making them less suitable for complex, data-driven tasks. The trade-off between accuracy and interpretability is a critical consideration in AI model selection, as highly accurate models like deep neural networks often operate as black boxes, while simpler models like decision trees offer more transparency but may sacrifice some predictive power. Balancing these factors involves choosing models that provide sufficient accuracy for the task, while ensuring that their decision-making processes remain understandable and justifiable to stakeholders. Model-specific explainability techniques are designed to unveil the inner workings of various AI models, from linear regression's coefficients to neural networks activation patterns, offering a tailored approach to understanding each model's unique decision-making process. These techniques, such as attention mechanisms in transformers and activation visualization in deep learning, provide insightful perspectives that help demystify complex AI systems, making them more accessible and trustworthy. Linear regression offers built-in explainability through its coefficients, which directly indicate the impact of each feature on the prediction, making it one of the most interpretable models in machine learning. Decision trees, similarly, provide a clear visual representation of decision paths, allowing users to trace the logic behind each prediction, which is invaluable for understanding and validating model outputs. Attention mechanisms in transformer-based models enhance explainability by highlighting which parts of the input data the model focuses on when making predictions, offering a transparent view of the model's decision-making process. By providing contextual insights into how different input elements influence the output, attention mechanisms help users understand and trust the model's conclusions, especially in complex tasks like natural language processing. Activation visualization techniques play a crucial role in explaining deep learning models by mapping out the activation patterns of neurons, which helps in understanding how different layers process information. These visualizations, such as feature maps in convolutional networks, provide a window into the model's inner workings, allowing researchers to identify and correct biases or errors in the model's learning process. Visualization techniques, such as heat maps and saliency maps, transform complex AI decisions into intuitive graphical representations, making it easier for users to interpret and trust AI outputs. By providing a visual breakdown of how models weigh different features, these techniques enhance the transparency and accessibility of AI systems, ensuring that stakeholders can comprehend and validate the decision-making process. Heat maps, saliency maps, and feature importance graphs make AI decisions more understandable by visually highlighting the most influential features in a model's prediction, allowing users to see at a glance which inputs are driving the outcome. These tools provide a clear and concise way to interpret complex models, ensuring that users can quickly grasp the rationale behind AI decisions and identify potential biases. Decision trees and rule-based visualizations offer significant benefits for AI explainability by providing a clear and structured view of the decision-making process, which is easy to follow and interpret. These visualizations allow users to trace the logic of each decision path, making it possible to identify errors and optimize model performance, thereby enhancing the trust and reliability of AI systems. Interactive dashboards empower users to explore AI decision-making by providing real-time visualizations that reveal how models process data, allowing for dynamic interaction and instant feedback. These dashboards enable users to manipulate inputs and observe changes in outputs, offering a transparent view into the AI's logic and enhancing user understanding. Grad-CAM is a powerful technique that sheds light on CNNs by generating visual explanations of model predictions, highlighting the most relevant regions in an image. By using the gradient information flowing into the last convolutional layer, Grad-CAM provides insightful heat maps that reveal which parts of the input image are most influential in the decision-making process. Grad-CAM highlights the most influential regions of an image by creating heat maps that show where the CNN focuses its attention during prediction, making the model's reasoning visually interpretable. This technique uses the gradient information from the model's output to the convolutional layers, allowing users to see which parts of the image contribute most to the final decision. The limitations of Grad-CAM include its inability to capture fine-grained details and its reliance on specific network architectures, which can lead to inaccurate interpretations. Improvements can be made by integrating multi-layer analysis and combining Grad-CAM with other techniques to enhance the precision and reliability of the visual explanations. Grad-CAM compares to other CNN explainability techniques like occlusion sensitivity by offering a more intuitive and continuous visualization of feature importance, whereas occlusion sensitivity provides discrete insights by systematically masking parts of the input. While Grad-CAM excels in highlighting relevant regions, occlusion sensitivity is better suited for identifying critical features through direct manipulation of the input data. Heat maps and saliency maps are visualization tools that explain neural network predictions by highlighting the areas of an input that most influence the model's output, providing a clear visual representation of feature importance. These tools transform complex model decisions into intuitive graphics, making it easier for users to understand and trust the AI's reasoning. Heat maps and saliency maps reveal which features contribute most to a model's decision by visually emphasizing the most impactful areas of the input data, allowing users to see at a glance which elements drive the prediction. This visual emphasis helps in identifying biases and understanding the model's focus, ensuring that the decision-making process is transparent and interpretable. Improvement techniques for heat map-based explanations include enhancing resolution and combining multiple visualization methods to increase accuracy and readability. By integrating advanced algorithms like smooth grad and guided backpropagation, these techniques can produce more precise and informative visualizations, making it easier for users to interpret complex models. These visualization tools can be applied to various AI models beyond neural networks by adapting the visualization techniques to suit different architectures, such as decision trees and support vector machines. By customizing the visual representation to match the model structure, users can gain insightful perspectives into a wide range of AI systems, enhancing their interpretability and trustworthiness. Decision trees and rule-based methods enhance explainability by providing clear, interpretable models that allow users to trace decision paths through explicit rules, making the AI's logic transparent and understandable. These methods offer a structured approach to AI decision-making, ensuring that stakeholders can verify and validate the model's outputs with ease. Decision trees and rule-based systems are inherently more interpretable because they provide a clear, step-by-step path from input to output, allowing users to trace the logic behind each decision. Unlike complex models, these systems use explicit rules and visual representations that make it easy to understand how decisions are made, ensuring transparency and trust. Ensemble methods like random forest and XGBoost balance accuracy and interpretability by combining multiple models to enhance predictive power while using techniques like feature importance scores to maintain some level of transparency. These methods achieve high accuracy by aggregating diverse predictions, yet they offer insights into which features are most influential, providing a compromise between complexity and clarity. Rule extraction techniques, such as decision tree surrogates and symbolic regression, can be used to extract interpretable rules from black box AI models, transforming complex predictions into human-readable formats. By approximating the behavior of opaque models, these techniques allow users to understand and validate AI decisions, bridging the gap between accuracy and interpretability. Interactive tools empower user-driven AI exploration by allowing users to manipulate inputs and observe changes in outputs, providing a dynamic and engaging way to understand AI models. These tools enhance explainability by offering real-time feedback and visual insights, enabling users to explore and comprehend the decision-making process with ease. Interactive AI explainability platforms like SHAP and Lime help users understand model decisions by providing visual explanations that highlight the impact of each feature on the prediction. These platforms offer intuitive interfaces that allow users to explore model behavior, making complex AI systems more accessible and transparent. Explainability-as-a-Service plays a crucial role in making AI accessible to non-technical stakeholders by offering on-demand insights into model decisions, ensuring that users can understand and trust AI outputs without needing deep technical knowledge. By providing clear explanations and user-friendly interfaces, these services bridge the gap between complex AI models and everyday users. Interactive tools help detect biases and improve AI fairness by providing visualizations and metrics that reveal disparities in model behavior across different groups. By enabling users to identify and address biases, these tools ensure that AI systems are equitable and just, fostering trust and accountability in AI applications. Model-agnostic explainability methods, such as SHAP and Lime, make any AI model interpretable by providing universal techniques that can be applied regardless of the model's architecture. These methods offer flexible and adaptable solutions for generating explanations, ensuring that users can understand and trust a wide range of AI systems. SHAP and Lime generate local and global model explanations by calculating feature contributions for individual predictions and aggregating them to provide a comprehensive view of model behavior. These methods offer insightful visualizations that highlight the importance of each feature, making complex models more transparent and understandable. Partial dependence plots, PDPs, illustrate feature importance by showing how changes in a feature affect the model's predictions, providing a visual representation of the relationship between inputs and outputs. By plotting the average effect of a feature across different values, PDPs help users understand the influence of specific features on the model's decisions, enhancing interpretability and trust. Counterfactual explanations offer actionable insights by illustrating how altering specific inputs could change an AI's decision, akin to asking what if scenarios. For instance, in a loan approval model, a counterfactual might show that increasing income by $5,000 would result in approval, providing clear guidance for users to achieve desired outcomes. Surrogate models act as simplified stand-ins for complex AI systems, allowing users to approximate and understand the decision-making process without delving into the intricacies of the original model. By using models like decision trees or linear regressions, they provide a transparent layer that mirrors the behavior of more complex systems, making AI more accessible and interpretable. Surrogate models function by creating interpretable approximations of black box AI systems, using simpler models to mimic the behavior of complex algorithms. These models, such as linear regressions or decision trees, offer a clear and concise view of how inputs are transformed into outputs, enabling users to trace and understand the decision paths. Decision tree and linear regression surrogates help explain deep learning models by providing a simplified representation of the model's decision-making process, highlighting the key features that influence outcomes. These surrogates break down complex neural networks into manageable components, allowing users to visualize and comprehend the intricate workings of deep learning. The challenges of using surrogate models for AI explainability include the risk of oversimplification, where the surrogate may not capture all nuances of the original model, leading to misleading interpretations. Additionally, ensuring the fidelity of the surrogate to the original model's behavior is crucial, as discrepancies can result in inaccurate explanations. Evaluating explainability involves measuring the quality and effectiveness of AI explanations through quantitative and qualitative metrics, ensuring they are clear, accurate, and actionable. Techniques like user studies and benchmarking against standards help validate whether explanations meet the needs of diverse stakeholders, enhancing trust and usability. Quantitative and qualitative metrics used to assess AI explainability include accuracy, fidelity, and user satisfaction, providing a comprehensive view of how well explanations meet user needs. Metrics like completeness and consistency ensure that explanations are not only correct, but also reliable and understandable, fostering confidence in AI systems. Fidelity, consistency, and comprehensibility of AI explanations can be measured by evaluating how closely the explanations align with the model's actual behavior and how consistently they perform across different scenarios. Techniques like cross-validation and user feedback ensure that explanations are both accurate and user-friendly, enhancing their practical utility. Techniques to evaluate whether an AI explanation is useful for human decision-making include user testing and scenario analysis, which assess how well explanations support informed decision-making. By examining the clarity and relevance of explanations in real-world contexts, these techniques ensure that AI outputs are actionable and beneficial. Future directions in explainable AI are being shaped by emerging trends, such as the integration of neuroscience and cognitive science to enhance model interpretability. New techniques like self-explanation and adaptive learning promise to revolutionize how AI systems communicate their reasoning, making them more intuitive and user-centric. Advances in neuroscience and cognitive science are paving the way for AI systems to mimic human-like explanation processes, enhancing their ability to communicate decisions in a way that resonates with human understanding. By leveraging insights into how the human brain processes information, AI can be designed to provide contextual and relatable explanations, making complex models more accessible and intuitive. New explainability techniques for generative AI models are being developed to demystify their creative processes, such as using latent space visualization to reveal how models generate novel outputs. These techniques aim to provide insightful explanations of how generative models transform inputs into creative outputs, ensuring that users can understand and trust the AI's creative decisions. AI self-explanation and hybrid human-AI decision systems are set to revolutionize transparency by enabling AI to articulate its reasoning in human-understandable terms. These systems combine the analytical power of AI with human intuition, creating a collaborative decision-making process that enhances trust and ensures that AI actions are transparent and justifiable.